Welcome to part 2 of Sensors, Effectors, Actuators. So here, the idea what I do is just kind of step a little bit deeper, as we've always been doing, dealing with more this physical side and seeing the complexity that's involved of trying to hook everything up. So last time we went through analog and digital signals and got a basic feel for some rudimentary sensors and effectors. And now we want to take the next step going deeper. And not going through every single thing that's possible out there, but seeing like, well, what is it like to then deal with a little bit more complex sensor? What kind of things should I be looking up? And then the same thing when it comes to the actual actuators and effectors. What is another one that we can learn and see a little bit more complex coding and keep stepping slowly forwards? So as always, shrink myself down, boop, 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 and we will get started. So as I mentioned, like last time, again, it was about analog and digital signals. So the fact of being that discrete kind of wave-like forms or the digital of on-off. And what does that mean for those signals coming in? What does that mean for you coding stuff and wiring and connecting things, especially when working with an Arduino Uno? We also learned about PWM, that pulse width modulation, which is to mimic a kind of analog output on a digital pin, which allowed us to do things like fading. So far seeing like fading an LED, but you're going to see later on how this becomes important for some of the other sensors that you hook up, especially when they're external kind of control boards. And even when it comes to things like servos, which we talked today about being like basic motors. So here we need to step and go a little bit further. Like, when we see sensors before, is like, I could spend forever in this course and in the future going through every different type of sensor out there, but that really won't help you. Is like every different project's going to need a different level of sensor and different controllers. You'll have access to different sensors out there in the market. And also, what is there available for code, tutorials, like how to hook everything up and work with them. But the idea is that based upon your project, you'll start looking up, well, what sensor would be good to detect the kind of information that I need from the actual environment. And similar goes for your actuators and effectors of like, well, what do you need to accomplish that task? What's available that your controller can do? What power requirements are there? And so forth. So when you start going out there to look for sensors, there are a lot. There's a wide range of stuff for light, motion, temperature, magnetic fields, vibration, pressure, sound, stretch of itself. But it really takes, well, what is out there? What are the quality of them? There could be different manufacturers and different quality levels from very high end to more basic kind of hobby or starting levels that we're working with. And you need to take all of that kind of things into account of what's needed and kind of keep checking out there. Find what examples you have. Because as we start building things up, like you're not going to have just like one basic sensor. Like you're going to want to have a range of sensors and effectors that to accomplish whatever you're doing beyond just, say, a basic rudimentary fading light example. You want to step this up. But then also be aware, as we've been talking about with controllers and everything, what limitations do you have? Like, what limitations do you have by power, cost, for what you can afford to get the project done with, what controller you're using, and what features it allows you to connect. And the fact that you're physically connecting stuff, well, what are the limitations of how many things you can connect? By physical spots you can plug them in, but also by things like power requirements and processing requirements. You need to take this into account. Okay, it's nice to have a bigger idea and maybe plan that out for the project, then find the right controller. But if you've only got one type of controller you can work with now, you need to understand, well, its advantages and limitations and kind of will work around those and see where you can build it. And as we step further into other types of sensors, they're going to require more things. Last time we saw basic ones that maybe just, hook it to the analog input signal and then just read the signal that it's sending in, or hook it to a digital pin to send information or to receive these things. Well, more complex ones are going to require more actual lines to communicate back and forth from those boards, and we'll be demoing some of that in the simulator version of this video and the physical version of this video. And when it comes to other sensors and everything else that are in the kits and whatever else you have access to, you need to understand that and like take it into account. I'm sounding like a broken record now just repeating that, but it is very important because previous times that I've taught this course, I've had people that come up with an idea but then forget, well, hey, we don't have sensors that do that. Like the requirements of those sensors, that they make all these plans for everything they want, but then they forget that, well, you can't plug that into the actual controller. We don't have a power source for that. So you need to think about these things as part of your project. Because like things, now if we go into sensors to start with, for example, and this really goes for effectors and actuators as well, is that each sensor that is attached requires some processing power and requires some actual physical power for it. So the more sensors you attach, the greater processing that's required and the greater amount of power that's required. Because as you've seen some of the basic examples as we work through with Arduino, that like, well, you're hooking it up and there may be libraries that do some work for you, but you still need to write your own code. And you need to also integrate it that you're like, well, okay, how often am I reading from that sensor? How long is this task taking to get completed? What does it take to do that work and that kind of processing that's required? So you need to take that into account of, well, if I'm adding in the sensor, what delays and time and processing is this also adding up? What power is adding up? So in the case for the Arduino Uno that we're working with, in the controller video, I mentioned some of the, like its specs, things like its processing power is roughly 16 megahertz. I mean, like roughly 16 million instructions per second. That seems like a lot, but what you get, like most standard computers are like 2 to 3 gigahertz, and that's with multiple cores, so meaning multiple processors. So you have a ton of instructions and more things that are being powered. So like being that microprocessor side and this thing, but the controllers here, we have these limitations. And like these processing resources are shared amongst everything that you were doing, like reading from the sensors, doing the actual computational kind of think work, sending out any requirements to the actual effectors or like actuators and what's required. And like the Arduino itself, as we said, is that power horse for controlling like lots of different sensors and working with the effectors and actuators, but it still has its limitations, and you need to take that into consideration. So simple sensors like the photoresistor that we went through last time that helped you measure kind of levels of light work by measuring the voltage that's provided by one analog socket in the Arduino, so one analog pin. You can do this by just calling the analog read function and having some kind of delay in between the actual reads and taking a sample from that signal as it comes into place. But like that's one sensor. As you add more complexity to it, you're like, well, how many is it going to take to actually read? What extra libraries and time is this going to actually take? So other sensors, like they're more involved. They require more specialized hardware and libraries. And these libraries add nice features into it. They take some time to learn and maybe require some lower level understanding or taking code examples and making sure you're reworking them to make sure that they work properly. Which I'll pause here as a second as I keep looking on websites for a lot of the example code that comes for Arduino. Is it seems to be a lot of the same passed around, and some of it's really not the best, the way that they've described it, the way that they've broken it down. And so if you're working with any of this code, it's best to try to break it down, find multiple tutorials, understand what are different things that need to be taken into consideration and how does this code actually work, and maybe turning it into a better format. And you'll see that in the simulator video and the physical work video that for one of the sensors for this week, I've reworked some code that I've seen on multiple different areas and broken it down and made it like just one basic function that you can copy and paste to work with that type of sensor. Boom. So now, like other requirements, if I'm going to start working with Arduino and know its limitations, when I start to work with other sensors, effectors, or actuators, you need to research them more before going on, not just download some random code example, plug it into Arduino, copy exactly the wiring they've done and see what happens. You've got to see, well, okay, they've probably provided some kind of schematic, but why those pins? Are there reasons why they've chose it? Can you move things around? And how do I hook everything up? Are there any additional like libraries that have to be installed into your development environment that help with the communication acts and working with those sensors? Like Arduino itself has a lot of libraries that come standard, but a lot of times when you're working with other companies, say like Adafruit, is that in the standard install, you're not getting those libraries, so you need to go through and either manually install it or use the actual library manager feature that's built into the Arduino IDE to download those new libraries to get that to work properly on your device. And then power requirements. Like, how much power is it going to need? Can it run from what the Arduino provides? Or should you be then looking into hooking up a separate source of power just for that sensor that's independent from the actual Arduino itself? And all that natural fun. So in the simulator and physical work, I'll be going through more of the code for another sensor. Now, as I said, like this course, I could spend forever going through a bunch of sensors. I may bring in some more in some future videos as we do like a project. We're getting into maybe a little bit more of the basic algorithms to try to connect all these sensors together. I may start introducing new ones so that you get more comfortable with using them. But you should be starting to look at, well, what's provided in my kit? What's in the tutorials? What other tutorials can I find that expands upon the knowledge that was provided? And how could these be used in a project? And just kind of play around and learn. And that's most of what I've done is, well, I started physically hooking it up, trying to understand the code, maybe being frustrated for a lot of the time, but coming back that every time I've done it, it gets a little bit easier and I've learned some kind of new skill or something I didn't know from the previous step. And that's more of what I want from this course, is people just to engage with this, because this kind of learning can continue way beyond this course. And there's always going to be new types of components and things out there, new projects, and maybe things that you want to build yourself. So in the simulator and the physical work videos, I'll be going through more of the code examples there. And what follows after this for the rest of the lecture is just trying to give some background knowledge on one of the sensors that we're going to use, which is a ultrasonic distance sensor that tries to measure distance bouncing off of objects using frequencies of sound. And then going into servos, which is something I always like to do, is your first little moving component. Compared to just having a light blink, is have an actual moving component and learning, well, what does a servo do for you? And that beginnings of trying to get to doing a little bit of stuff with motors and these things that especially require more power. So the rest of these notes kind of goes into background information on those and things that you're like, well, when you're looking these up, you should try to look up similar things. Because every sensor is going to be different. It's going to have different levels of complexity that what you're able to work with and what you can modify and do and build into a project. So the sensor that we'll be going through this time is called an ultrasonic distance sensor. And again, there are a wide range of these out there. Wide range out there. But the one that you see here to the actual left is a common one you'll see on projects. And it's very funny because a lot of times they place it to kind of humanize a moving robot because it looks like two eyes. But it's not. It has nothing to do with vision at all. It's more about beaming and receiving information and using sound. Now, when you're looking at these boards and some of these sensors, they're going to start having more technical names. So yeah, this is an ultrasonic distance sensor, but specifically its classification is HCSR04. Now, why? I don't know. That's just the name they pick. And most times for the ones who are working with Arduino, you'll see them on here, so on the front or back, and you're trying to look, when you look at sensor, but you're not sure what it is. The kits you can look up, they got pictures, but if you're not sure what it is, most times there'll be indicators or markers of some kind of name that you can then search and find a whole bunch of other examples. So you have to be careful that the rest of the work that I'm talking about is specifically this HCSR04, that sensor. If you see other ultrasonic sensors, it may be a similar idea, but there's different things that you need to do to actually write the code for it. What advantages and disadvantages does it give you? Now, this one specifically, you'll see in like every Arduino kit out there and lots of projects with different controllers because it's cheap and readily available. So its size, its weight, what it does is basic. And it's not super great, but it still is very interesting. And we need to understand, well, what limitations and what can it do for you. And so I said here, it has nothing to do with sight vision camera stuff. That's a very much more specialized kind of controller board or hooked up to more of a microprocessor to do work with that. This one just does sound. So it's economical sensor that provides between 2 centimeters to 400 centimeters away of non-contact measurement functionality, so that when you communicate to it, you can ask for it and get a signal back and kind of determine what's the distance of something that's in front of it. Not all objects, but just something that's bouncing stuff. And before we go to the other notes, you kind of think of it like, you see there's two things from it. It's basically, one is a transceiver, one's a receiver. So one emits a sound in a higher frequency than we can hear, and the other one is then waiting for that sound to be bounced back, and then based upon the actual speed of sound, you can roughly calculate, well, what's the distance, the time it took that sound wave that was sent back to be received, and well, what distance do you have? Now, the first thing, limitations from this, is that it's only good for about 2 centimeters away from the face of these. Right here, so from the front of these, 2 centimeters away to up to 400 centimeters. So anything below 2 centimeters, you're not going to get accurate readings. So something if it's touching right to the ultrasonic. Or if it's further away, and trust me, even at 400 centimeters, like that's roughly 13 feet, the further you get away, the more other things that could have an effect on it. Even the time it takes for that sound, which is fast, but like you're doing the readings, like takes longer to come back right in the relative terms for speed of sound, which is already freaking fast compared to speed of light. But like at 13 feet, more things could go wrong further away. So where do you find a range of what works for you? And the fact of like other things that affect sound, like sound bouncing off of stuff. If you have soft, foamy material, it kind of absorbs sound vibrations, but then if you have other kind of like shiny materials, or even my office here, which kind of is like, my microphone's not always the best because it echoes off the walls, is how sound bounces around off those and how it hits and how things hit at an angle. All of that stuff needs to be taken into account, but hey, it's a beginning starting one. If you know these, well then you kind of try to modify your code to not expect exact measurements, but close within a level of tolerance, and then combining that with where you physically place the sensor on the robot, what will actually happen. So, uses sonar to determine the distance. It offers like non-contact range detection, so you're not actually touching anything, and it comes complete with the ultrasonic transmitter and receiver. So the idea is that this is a separate board from here, that it's not just like when we had the photoresistor, which we had to hook up another resistor to make that voltage divider on it, and same thing with the kind of button, is that everything here is built into this. So you're getting an entire circuit and everything, that you can see that you have this board, you can see that you have the conductive lines below an insulator actual material, you have exposed pins, you can see markings on this one, which is giving you ways to understand what's there. We can already see that we have G and D for grounds. You know, well, this pin's got to be something with or negative or ground from right here. I'll give it away that the VCC means power from this. And then we just have these two other pins for meaning trigger and echo, which we need to learn more about. You get things like other circuitry here, and even if you look at the back of it, there's more integrated chips and everything that's built into it. So this is not just one sensor, it's a combination of sensors into one little device, which then gives you one way to communicate to it and receive information back. That you can trigger to have one action for it to do the pulse, and then to actually wait to receive information to come back from it. So again, this is like multiple things built into one to give you kind of a next step, so a step up, and what you need to do to plug it in. So when you're sitting here and you're looking at other sensors that are out there, you need to, well, get the name of it, what is the cost it's going to be, what libraries are out there that can kind of help you understand, so tutorials from here, and these names and things are a starting point to help you. But next is to understand, well, what's the breakdown of what are you seeing for like these pins? What do you expect, and how do I have to hook it up? So you need to find some kind of wiring diagram and understand the components. And you can see from this one, from the points, is that like, and we've got the VCC, like the voltage, it's saying that right here is like, okay, plus 5 volts. So we're good with the Arduino. That's providing enough. Anything higher, like we'd have issues. But we know, okay, this should be fine. We have ground, so 0 volt or ground, we're fine. You have the two receivers, the transmitter and the actual receiver of the ultrasonic wave. This thing you don't have to worry about too much, but it's kind of like clock ticks for stuff, a quartz crystal, like a Timex thing. A Timex watch, I mean, and maybe I'm dating myself for much older. If anyone remembers what Timex is and any watches along those lines. Okay, either way, I'll stop with that. And okay, I've got a trigger and I've got echo pins I need to connect. Doesn't give me more information to get to the Arduino yet, but it's that first starting to understand what are the components, what I'm working with. And I have to know, like, well, how do I face this? Like, where is it coming out of? The fact that, like, well, if it's a sensor, where, like, what components have to be angled what way if I'm placing this into some kind of object. And the fact that these are forward facing, that one is going to beam it out like a speaker and one's going to receive it. This is the front side, and so you can then determine, do I have this at an angle, straight forwards, down, upwards? Depends on your project and why you needed that distance information in the actual first place. Other information to know about is things like what's its power supply and other terms here that you don't need to memorize perfectly. Most times when I see a new term, I just try to Google it and see how it's defined and see what information I can find about it and kind of add to my knowledge base as I keep growing projects. But like, okay, well, for this sensor, power supply needs, 5 volts. Hey, good. Direct current. And okay, good. That our Arduino actually does provide that. The quiescent current, and I'm probably saying that completely wrong, but I'm perfectly fine pronouncing things wrong until I learn better. And this means when I looked it up was more about, well, how much power is roughly when it's starting up? So, because you have like when you're first doing things like how much power is it going to draw? And this is less than 2 milliamps. So remember here that we're talking about voltage and current, that current being able to run stuff, is that when this first starts up, it's going to only need less than 2 milliamps to actually start up properly. And then its working current, so while it's actually doing work, is drawing 15 milliamps. And so, like, this should be fine. I don't have in the back of my head right now the power of the actual Arduino Uno, but I would just look that up on some kind of spec sheet if I needed to. But I know that we have at least an amp going through that, and so 15 milliamps is much less than an amp in this case, so we're okay. But we know that, well, this ultrasonic is going to take that. So if we threw in 2 ultrasonics, if we're even able to connect that to our controller and use that, well, then that means that's going to be a total of roughly 15 milliamps that this is going to be drawing, and like that's more power consumption. So well, even just having 2 sensors, throw in some actually effectors and actuators there, going to be more drawing of power and could cause issues. And so like you're up to that max of power, causing power for like how much power the Arduino can provide. And if it's plugged in by USB, well, you got limits. If this is by battery, it's like, well, that's also going to affect how long the actual battery source you're using is going to actually last. But you need to look it up. So most times with these sensors, start looking up, okay, well, what are power requirements of it? Are there any spec sheets or data sheets, as they're called, for talking about this? Or are there even just posts on other websites where people have talked about this? I can get a rough idea. And going deeper into this, if you have more experience with electronics, you can start using different meters to actually measure the actual, like, well, in different scenarios, what's the actual current requirement of this device, and do your calculations there. But we're starting basic, and you should at least take into account how much does it need. Because remember, if something's not working right in your project, these are one of the things that you could take into account. Of like, well, how many things do I have connected? How much current does each need? And is this overtaxing the actual device, which then is causing issues? So other things like placement and stuff that can be specific. So here, like the effectual angle. So this is the maximal angle at which an object can be placed from the center of the sensors in order to deliver an accurate reading. Because now we're going to get sensors, and we know, like, from the actual environment and the quality of the sensor we're dealing with, that, like, these may not be as good as you think. Like, you can't just think, okay, this is the exact measurement, this is exactly what's going to happen. You're like, well, no, I've got a measurement coming back, and there could be issues. So from here, it just means roughly that it can be at a 15-degree angle, whatever object you're measuring. If I have the ultrasonic sensor and something else, once you start getting something to be angle, you have sound coming that's then going to bounce off in like different directions. And it may not actually, when it beams up from the transmitter, the receiver may not actually accurately get back enough of a sound level to determine the proper actual distance. And if other things are affecting, if there's other ultrasonic sounds in the actual area at that time that kind of match up for some reason, could screw things up. And even like movement, because again, if you have the sensor and if it's rock still, you're okay. But if it's on a table and the table moves, well, that center shifts roughly from what it's getting, and so that's going to also affect what's going on. And we'll see during the physical work, I'll see what happens if I move my own desk table here. Does it jitter or change somewhat, and how do you deal with that kind of changes? The ranging distance, this means for this one is 2 centimeters to 4 centimeters, so roughly 1 inch, less than 1 inch, to like that 13 feet kind of away. But you expect the closer it is, it's going to screw up. The further away it is, it's not going to be as accurate for these ones. Other ultrasonic sensors out there can give you a wider range of what they expect, more accuracy, but they're more expensive and require more power. Now, resolution here means, well, how accurate is it going to get? And so here it's saying within 0.3 centimeters. And now this is where it can be off. So it'll give it back. Based on the calculations and what you're doing, things could change. You're going to see in the simulator video versus the physical work video that I'm getting different levels of accuracy. And again, these are the issues of simulators versus the physical work in the environment that you're doing stuff. And so here, like you'll see those demos, but that resolution, like, well, it's within 0.3 centimeters. If you need something that need to be way more accurate, well, then you're going to have to go look for a more expensive sensor, maybe a better controller at the same time. Measuring angles where you can put stuff at. These other ones are like the dimensions and stuff and how big it is. Can you fit it into your project and those kind of requirements? Because maybe you're trying to fit this into a smaller container of some sort, and this is going to affect things because you have limited actual space to fit the wiring and doing everything else. Something we haven't actually really directly addressed yet in this course beyond just doing the wiring is how do I physically, once everything's wired, physically put it into something from there. I should probably take like a breath. I always talk so fast and actually like take a sip of water before we continue. So, I said before is that the ultrasonic sensor uses like sonar to determine the distance to an object. And it goes through roughly like 3 steps. Is that the transmitter or trigger pin sends a signal from that point in time. So this is more from the controller to this device, is that along the trigger pin, a signal is actually sent, and a high frequency sound is then emitted at that time. So you can see that from the diagram right here. When the signal finds an object, it is then reflected back. So that's like that sonar sound, kind of like a bat. It's going out, that sound is then being bounced back. And so at the same time as the transmitter is sending out the signal, after that, then the actual like echo pin is then waiting, and like a receiver is waiting to receive that sound back on that same sound frequency from here. And then based upon the speed of actual sound, you can roughly then determine actual distance. So it's those 3 steps. So signal sent to the trigger to trigger the emission, then the device automatically sends out the actual sonar, the receiver is waiting to receive it back, and then that receiver along the actual echo pin is echoing back that transmission of that time. So the time between transmission and reception of the signal allows us to calculate the distance of that object. Okay, since we know the velocity of sound. But as I said, like, you're going to have problems. I think that you'll see these more, not in the simulator video, but definitely when we go to the physical work video, I'll be showing some different materials that are in front of it, different shapes, different angles, my own hand, and what happens. And you can see, using the serial monitor and the serial plotter, some strangeness occur. But you need to take into account that soft objects will absorb sound, and so it means that frequency and what's coming back, it's going to be different, and so that's going to fluctuate from the actual sound itself. If the object's too far, if it's at an angle, and vice versa. And these are known things of just like if you look up tutorials, they talk about these in videos with it for these basic sensors and beginning from there. And it's a known thing you need to take into account. So you have to think, well, what environment is this device going to be working in? How accurate based upon that environment is this going to happen? And what fail safes do I have in place to deal with that if possible. Because the fun part with a lot of robotic projects is that you code it with one intention, the way it thinks, and it's just going to keep reading that sensor data from the environment and react in the way that you've programmed it. And so if the sensor data doesn't really reflect the real world environment, that's when things start going haywire. Okay, so that is the basic ultrasonic sensor. That's a new one from this time. And you can see there's more to it. There's more that's built into it. And you'll see that when it comes to coding and wiring, there's more that's actually required from here. And it's that first thing I said, again, like if you're looking at a new sensor like you should be doing for the future, you have to look for all these requirements. You have to do some kind of research with it. Now, the next thing I wanted to introduce is, as I said, is servos, some kind of motor moving mechanism. And honestly, when I started doing some of this, I still say like this was one of my favorite things to work with because I don't know, it just felt interesting to me to write some code and get something physically moving in front of you beyond just the light actually flashing. And servos are one of those beginning easier ones to start with, and the next is having motors and thing beyond that. And really this is just like a self-contained other device that has a motor in it, but a little bit more fine-tuned, controlled, and stuff that's kind of dealt for you. And a whole world of servos, and once you start working with them and you hear that sound of that servo, you'll realize you probably have heard other devices that have servos in them, especially remote-controlled vehicles will have servos in them, and it's distinctive kind of gear rotation sound you'll kind of get used to. So a servo mechanism, or servo, can refer to quite a few different machines that have been around for a larger, like a longer time. The ones we're dealing with, we'll talk about like angles and moving, but you have anything where it's more of that effector of moving something to a specific angle or back and forth, but controlling the positioning as you go. And not just something that just spins or just clicks and just keeps spinning in one direction, that you can move it to different precise ones. So a servo is any motor-driven system with a feedback element built in. Servos are found everywhere in heavy machinery and like other places, and then like different levels of what you can do with them. And you see like a wide, like not a wide range, but like some of these hobby RC kind of servos to the actual left here. And the blue one that you see here is I think it's probably the exact same one that we have in the kits. Now, for this one, I always like to use some videos. I'm trying to work them in where I can. And this gives you kind of like a basic introduction talking about servos, and I'll go over some similar information from the video and then add a little bit more to it.
Hi there, Spark fans. Rob Reynolds here, and today I want to talk about servo mechanisms, or servos as they're more commonly called. The servos are one of my favorite components of physical computing. They can be programmed and just left to run on their own, basically sweeping back and forth. They can be controlled manually, and they can be triggered by virtually any input. And the output is precision positioning. They're used for steering RC cars and planes. They're great if you need repeatable precision movement. And they're perfect because of their lightweight, small size, and high torque for things like animatronics, particularly faces and eyes. Today I want to talk about some servos, just the basics basically, show you a couple of projects, and hopefully inspire you to figure out ways that you can put servos into your next project. Servo motors generally come in three sizes. There's micro, there's standard, and there's jumbo or giant. All are controlled the same way with three wires. There's power, usually 5 volts for a hobby servo, ground, and control. And control is done via PWM or pulse width modulation. The servo expects to see a pulse every 20 milliseconds, and the width of that pulse determines the position. If you were to take a servo apart, and if you have one that dies, I highly recommend that you do, you would find a small DC motor with a bunch of gears, a control IC, and a potentiometer for positioning feedback. There are also 2 stops that limit the position to 180 degrees. Now, one thing we haven't talked about yet is a continuous rotation servo. In that, those 2 stops have been removed, allowing it to, as the name would imply, rotate continuously. Now, the trade-off is that you don't get positioning feedback. You can control speed and direction, but not position. Now, let's take a look at one. So as you can see, I'm controlling direction and speed on this continuous rotation servo, but like I said, the trade-off is position. I have no idea what the positioning is, which for some things might not be terrible. If you want a camera that sweeps the room, you could certainly use something like this attached to a pulley with a slip ring. The continuous rotation servo is controlled just like a regular servo with servo.right. However, with a normal servo, you would send it a number between 0 and 180, and that would determine its position. Whereas with the continuous rotation, the number sent is its speed, 90 being no speed at all, and then the further you get, either down or up from 90, determines how fast you go. Further away, faster speed. Servos, like I said, can also be controlled manually. And they're great for robotic arms like this one. Now, something like this could be programmed to reach down, grab something, come back up, move it over here, and drop it in a container. Now, as we all know, you shouldn't be touching your face with your hands, especially during cold and flu season. The problem is cold and flu season is also the dry season, and your face gets so itchy. What to do? Well, as I said, servos are great for robotics and can be triggered by virtually any input. In this instance, I'm using the SparkFun Quick Proximity Sensor to trigger it to scratch my face without actually touching my face. Ah, that's the stuff. So that's just a tiny sampling of servos. If you want more information, check out our Basic Servo Control for Beginners guide or our Servos Explained page. Then start figuring out where you can add precision movement into your next project. Happy hacking, friends. Oh, that's the stuff.
Okay, now I do have to mention that that video is kind of ironic due to the timing of me recording this video during COVID time. So that SparkFun video was actually recorded before COVID hit. So I think it's very ironic about the not touching your face and using a robot to do it instead kind of solution. But you get that first introduction of kind of servos integrated into something. And that's multiple servos. That when you saw that hand, really they had a different structure and they were recreating the idea of tendons. So there weren't something individually controlling each knuckle in the finger. Is the fact that there was just a hinge, there's a string, and when the string or elastic is pulled, like your tendons in your hand, they are actually reacting. And so then it was servos that were controlling it. Same as the little gripper arm, and just, you know, the one that they have there is a very common model that I've seen kits for online and for 3D printing the pieces. That one has multiple different servos, things that are controlled. Is like when it's opening for the actual like gripper arm, that's a mechanism connected to a servo. The same to actually swivel things around and make it go up and down. And so it's that combination of an actual actuator and the physical body combined together into the controller, and using theirs, you can see that he was just using basically potentiometers as a way to manually control different components of that arm. But you could take out those potentiometers and just put in your own code to control that actual device itself. So servos are a nice first starting point, but it's not that like instantaneously one servo is going to do everything you need and it's perfect. We are now dealing with the physical world, so torque, friction, and it's power and the properties of physical material and wear come into play. And so everything that's in this device may be limited. Not like the ones we have in the kits, they're not going to be able to do a lot of stuff. They are basic, they can be broken, they wear down over time, but then there's more like the ones that are a little more costly, but they give you more abilities depending on what you want to do with your project. Now, when you break them down, they generally have an idea of like internally. It's another device that's built together, just like the ultrasonic sensor, that now this is a device that offers like multiple things that are built in that gives you then a way to interface and control with it. So you get things here like a DC motor. What they mean by DC motor is just a direct current, and usually these are very basic ones that they have a lot of wrapped wires on the inside, and the idea is that when you run current through it, it creates a magnetic field in a specific direction, and then there is a specific shaft in the middle that will actually then rotate in the direction of that field. So based upon how much power you give it, it will start actually rotating. So that's your motor right here that's actually doing the moving, but then it's connected to gears that are up here on the top that handle stuff for torque, because that DC motor with that spinning, it can't handle like torque or friction on it, but the gears then help translate that. So this is different size gears, different size teeth that are then connected to this external part that will actually move, so that you can control the movement and you can also deal with a little bit of the torque issues, but you have those limitations. You also have internally here another microcontroller or some kind of special integrated circuit for this that handles basically the in-between of controlling the actual motor, getting some feedback information, and receiving signals from some external source. That could be your controller or some direct circuit that you've hooked this up to. And then you can see this one here, and it may not be the same in every device, but talk about like something for measuring the actual, like how much has something moved. And this is that feedback here, and they're saying they're using a positional potentiometer. And again, if you remember from the previous videos, a potentiometer is a variable resistor, so it changes the actual level of current, which is something that can be picked up. So what you're seeing in a servo itself is already a very, very basic robot. In that sense, a component of you have the sense, think, act. That you have the sense being the potentiometer to keep track of knowing how much the actual servo end is moved, so what position it's at. You have a controller then that can detect that position, and then you have the actual motor itself as the actual actuator and effector to make the changes. And so that controller then, based upon that kind of input, is doing that robot cycle to get to that proper point. And you also then have external input from the other environment by whatever the external device is that's sending signals to this microcontroller. So it's a little bit more complex, but it's going to be in that one little package. You'll see the servo box. You have the insulator on the outside trying to protect everything, and good enough to work with. But you need to take into account now, well, when I'm doing this, this is almost the equivalent of doing work with someone else. You have one controller being, it's going to be for us Arduino Uno, that's then communicating to the controller integrated circuit that's inside of the actual servo itself. And we'll be doing this through a library, and our code will make it easier, but you have to realize, well, that is a separate controller that once it receives its signal, it's working asynchronously at the same time as your controller. So this is not tell the servo to move, my code will sit there until it's actually moving and then be done. Is, well, you've kind of got to be like, oh, I wait for a bit before I move on to do anything else if I'm expecting the servo to be at a specific position before any other work continues. So you need to take that into account. So the DC motor is attached to a gearbox and outputs a drive shaft to increase the speed and torque of the actual motor. The DC motor drives the output shaft, like you expect. And so these gears are going to be important. I'm going to talk about it later. And like the fact they're one of the points that can be worn down, that too much torque or force on it will strip them and break and destroy the servo. And I won't be doing that because at the time of the recording of this video, I have only access to one servo, and I'd like to not destroy it. Maybe in future versions of videos if I get my hands on other ones, you can see what happens. Yeah, so controller circuit or integrate signals that are sent to it by the controller, and the potentiometer acts as that feedback again to that controller. So all these things that I kind of already went through. Now, nearly all hobby servos, so these very basic ones that we're going to be working with, have a standard 3-pin kind of spaced apart kind of connectors. You won't see it here, but you can see the wires that are coming off of them. You'll notice them here that there's 3 pins of being ground, power, and like a signal that's sent to controls information. Because like this is a separate controller, it doesn't have any power sources built in. You need to provide that power either through the Arduino itself or through some kind of external power circuitry. But then you have a data line that has to be connected to your controller to send information about what direction and what position should the servo actually move to. Now, like all of this, now here, be aware that this is extra information on these slides. At a lower level, there's a lot more that's going on that needs to, like when you're sending signals at a specific rate for the other device to actually like interpret what's happening. And if you go further into electronics and lower end and more electrical engineering stuff, then you can understand what's going on here. We'll be working in the libraries where some of this stuff has already been handled for us. But the most important thing you need to be aware of is that data line, you have to connect it to a PWM pin. Like it needs a pulse width modulated kind of signal coming in a specific way. And so you have to connect it to a PWM pin. And for us, we're going to be using then a library that's built in, and we have to understand, well, how do we work with that library and what advantages or disadvantages does it give us? one great advantage is making it a lot easier than dealing with the low-end signals and just getting us to keep moving forwards. Now, powering a servo, so depending on the size and torque and output of your servo, we need to worry about this. Like standard ones we're working with are going to have 5 volts, but other ones could require more. So you need to be aware of, well, when you're getting these servos or the ones you have, what are their limitations, and I've said this so many times, like what can you do and not do with them and what do they require? If you're going to go for bigger servos, you're going to expect into this, well, that's going to require more power to get the work done. And so will your Adreno do that, or do you need another external power source and all the requirements from that versus smaller ones, and what happens, and maybe external extra power sources. Now, more important than the actual voltage is the current. So how much current will that motor actually draw? And when it comes to motors and servos, it's like these are going to vary because you get terms like if it's loaded down or unloaded. And this just means like, well, if it's just a servo moving and there's nothing for friction really much affecting it, then, well, you don't worry about it too much. But if there's something pulling against this, like you've attached this, like that, like I said, that hand that was in the video, that you have a servo moving and it's pulling against something that's resistance, and that may take more energy as it's doing its actual work. And so the actual current draw could be different. That could start out fine, but if it's under like a heavy load, there's a lot that it has to actually pull. It may at that time start pulling more current to get its actual work done, which then causes issues along the circuit if you haven't dealt with that, like something that can handle that extra current flow. I've seen this sometimes, and like I don't have enough motors here at the time we're recording these videos to demonstrate it, maybe in the future, but you get enough motors and things going, you see the whole Adreno, the lights on itself just dim because suddenly the motor's pulling a lot more power, and then everything else can't do its overall work. So with these basic common hobby servos, it's about 10 milliamps, but larger servos would require more. And so you can start seeing these things adding up for the actual draw. And like that 10 milliamps could change. It could be less, it could be more, depending upon the actual load and at the time of doing that work. So if we brought in things like an ultrasonic sensor and then working with, say, one servo, well then, remember it was roughly 15 amps for that ultrasonic, 50 milliamps, not 15 amps, and then 10 milliamps for this one servo. So there you've already got 25 milliamps, and that starts adding up as you're doing more work, let alone the actual what's required by the actual Adreno device itself and anything else that you have hooked up. So it starts adding up. So it's important to check the specifications of your servo you intend to use and make sure that your power supply has the proper voltage to deal with it. Servos draw considerable power, and if you need to drive more than 1 or 2, you'll probably need some extra power sources. Like if we're working with a basic Adreno, I'd say really only like 1 to 2, as long as you don't have a bunch of other sensors really hooked up to it as a starting point. But as soon as you start hooking up a bunch of things, well, maybe you need to have that external power source actually connected to this and then be controlling that. The one thing from right here is just to make sure that the ground from the Adreno and your external power source are shared. So the power will be different. Like you don't share the power lines. You have one power line going to the actual like power source, and you have one common ground then that's shared, that you connect the ground from the Adreno, whatever line, and some of the other one, common to complete that circuit. There's an example at the end of the slides here. Now, other types of servos is once you get out there, like it's more like this is the same thing as all these new sensors I talked about, is that you need to look up information about them. Like, not just the one basic tutorial and not one thing on Stack Overflow or Reddit or whatever you've gone to. Go to a couple of them. Like, I've generally found a lot of the same code gets copied and pasted, and when there's errors or like really bad explanations from there, they don't get fixed. You just kind of copy and paste without really trying to break down and understand what's that code. So look at multiple different sources and try to bring that together. Look at multiple different code examples, and especially when these different code examples provide something different. Like, why do they provide that? Maybe one gives a better explanation versus others, that usual kind of like gathering of knowledge fun. But when it comes to like your rotors, you're gonna the standard like servos, you're going to have kind of 2 different types roughly, like the ones we're dealing with that move in different directions. Either get the standard hobby servo like we have in the kits, that is it moves between angles. is that it'll tell you. So it's not going to be something that rotates completely like a motor, is that you have a limited range. Usually it's 180 degrees. Sometimes it could be smaller of that 90 degrees. But the idea is that you can then move it along that 180 and you can tell it, hey, go to degree 60, and it will move to that degree 60. So using that potentiometer can tell where something's moved and then stopping. That closed loop cycle from the beginning. And then you can have it move backwards and forwards from right here, but it will not spin all the way around. But what you can also get is then continuous rotation servos. So what this means is that it's not just that 0 to 80, is that it will just always spin. You can go backwards and forwards, and this is less about getting it to go to a specific angle, but kind of working like a motor where you get a little bit more fine control from it. So the signals you send to, instead of saying what angle, instead it's like what direction, if it's forwards or backwards, and enable you to easily control how fast the drive shaft is actually moving. So sometimes I've seen these continuous servos used in other moving robots to give more precise control, but then you're connecting it to things like on the outside to wheels and everything else and friction and what could happen from there. If you were to break down more expensive remote-controlled vehicles, you'll generally find that they'll have these servos in them for precise control of different things. Now, sizes, you get tons of them out there. That you get very micro, small ones, to medium-sized, to giant ones, and all require different levels of power requirements, have different levels of torque, and what they provide for you, and cost. Beyond just sizes, you'll also get different shapes. As I said, most of them we're working with here is going to be these standard kind of square ones, but sometimes you get ones that are like linear servos, that instead of being a rotating arm, instead is that when the motor kicks in, it moves something backwards and forwards along one track. So useful depending on what you're trying to create. Now, each type has their own benefits and drawbacks, and it said, like, you want to take that into account. Like, we're going to work with the micro ones because they're the basic ones. They're starting one. They don't have a lot of torque for what you can do with them, but they work okay for how much power you need, and you can build up there from your project. But you expect of, like, you're not going to see a small micro servo or a standard size one in a really large robotic arm if they're being controlled by that. You'd see more of these giant servos within them with larger power requirements and combining and bringing everything else together. Now, one of the other components I mentioned before was gears. So the gears in this, again, I said, that's controlling that torque. And this is physical materials. So cheaper ones, and like the ones we have in the kits, will generally be plastic gears. It's cheaper, easier to make, but this is plastic that, again, it will bend. It over time, if there's too much torque on something, friction, it's going to bend, could end up breaking some of the actual gears, or they'll change and wear down. So you will get plastic versus metal gears that are out there. So inexpensive servos, generally plastic, but they can strip them and then boom, you're done. Like even you playing with them could strip them. But the metal ones are more expensive. So like if you're doing a basic project and you're not expecting there to be a lot of torque beyond the requirements of what it says for the actual device, then you're okay. But if you do expect more, well then maybe investing more money for just those components, ones that have metal gears in them, will be better just because it can handle higher levels of actual torque in that design itself. So that balancing back and forth. Now, accessories. So servos themselves are like nothing until what you attach to them. You can see this one right here. This is a much larger one. I'm going to guess this is most likely more expensive and has like an actual metal gear inside. But you have the shaft that's up here, and most all of them are like this, that they kind of give you one smaller gear that you can then slot things into as long as they match, and then connect to, because this will be what rotates backwards and forwards, and then you're attaching different things down to it or onto it to get the work done. A lot of times when you buy servos, or if you have ones with kits, they'll come with these kind of plastic tops here that have different holes that can be screwed in. There's usually a little spot for a screw in here so that you would take one of these bottom pieces, you would slot it in, and then you would use a screw that's provided with it, and a very small screwdriver, to lock it in place so it doesn't come apart. Most things we're doing, like, you can just connect in. These holes that you're seeing through here is then so that you can cut or stick or tie things in through it to actually attach stuff to this. So maybe metal wires so that when this arm moves, it kind of like causes something else to move. So this is the physical design component stuff we still haven't dealt with in the course. We'll only get to a certain level, we have a certain amount of time. But then you can start designing, connecting your own other stuff to that top and that kind of placement, and this will become into what you're actually building. So you want to look at what can you make, what could you build, how could you attach from this, and where would you place things. Okay, getting into Arduino specifically as a way to control these servos, because there are other ways, but like if we're doing this, we're going to be generally using the servo library that's built into the Arduino language itself and handles things for you. I'll be explaining this more here. This is some of the syntax of how to include a library that's built in, so like you're importing and everything else. So it brings up, but like this is the first step of understanding that you need to look deeper than just copying the code, understand that there's limitations in there. That like this library itself, can support up to 12 motors on most Arduino boards and 48 on Arduino Mega. So it's not saying instantaneously that I can suddenly throw in and I'm going to be able to connect 12 motors to every single controller that's out there. It just means this library itself has that capability, but then you still need to worry about what are the physical limitations of the controller you're working on. So the Uno is smaller. If you look up the Arduino Mega, it gives you way more pins and connectors to be able to actually do work. But even there, you're still limited by how much power and maybe that other circuitry that you need to use. So you can control this through this. And this could even be that maybe you have an external board that makes it easier to connect a bunch of servos to it, provide extra separate power, and then having it communicate to the main board and then having the library control those other servos from there. So it's limitations. Another very big one to know about is that on boards other than the Mega, and I've tested this on mine, you should test it on your own because things always change with different designs and versions, but on mine so far, it like the analog write, so the PWM on pins 9 and 10, so pin 9 and 10 on Arduino Uno are PWM pins, and so now those will not work with analog write. They're just disabled. Don't ask me why. I didn't care to dig deeper into that. If you can, go ahead and have fun. Send me the information. I'll include it in future lectures. But, it just means that, whether or not you have a servo on that pin, that analog write won't work from right here. I don't know what would happen for digital kind of signals along those lines. Like maybe it'll work fine for digital and won't have any effect on anything else. But really you need to take into account, it's like, okay, well, if I'm using a servo and I've got the servo.h, even if I've only got one servo for my project, well, pins 9 and 10 will not work to do anything for fading lights or other things that require PWM pins where I will be sending an analog write. So my suggestion is if you're going to start using servos that are directly connected to the Arduino itself, connect them to pins 9 or 10. So, and generally at most you're going to have like 2 servos directly connected to Arduino. Anything beyond that for the micro ones, I suggest like having a separate power source. So connect them to pins 9 and 10, and then for the rest of your project, any other sensors you're connecting, is you cannot then use 9 and 10 to do analog writes if you want to control them. So no more fading lights on a 9 and 10, but any other PWM pins, you're good to go. So fun parts, but this takes some of that research of, again, limitations and weird things that then pop up. Okay, other code that you're actually going to see in that library is there's an attach function. Just like we had before where you did the pin mode of input or output. Here instead then you've got to first include the actual library, so at the very top, so hash include from right here is the C, C++, and this modified version for Arduinos, and then servo.h with the angled brackets here indicating it's a built-in actual library. After that, in your global variable section, you'll be declaring a variable of type servo and then giving it whatever name you want. This name, it doesn't matter, just this here because this is the type. And for every servo that you're going to be independently controlling, you'll make separate variables. So this code here is only good for one servo. In your setup function, then, you'll be taking that variable you declared before and going .attach, and then the pin that it's actually attached to. So in this case, 9, one of those used up pins. So 9 or 10, and then you could use others. But again, stick to 9 or 10 if you're using the first one. So that's just to say, okay, for this one, saying that that's kind of like your initialization of that actual servo itself. The next useful function is the right. This is then the way that you tell a servo what angle it should actually move to. So here in this example, what it is that this is for the standard hobby servos. If your servo for some reason starts spinning all around, you don't have a standard servo, a hobby servo, you have a continuous servo. And why do I mention this is I've bought stuff for the course before that they were all the same markings, but either due to me not understanding something or the manufacturer I got instead was they were marked to be hobby standard servos, but instead they were actually continuous. So this same code that I used, the whole thing started working differently. So again, if it spins all the way around, you've got a continuous servo. You don't have the normal hobby servo. But either way, so for this example that's right here for setup, it means it's connecting one servo to pin 9, and then at the startup, it's telling the servo to move to 90. And there's no other delay. So I'll explain this again here before. It's sending us its signal, and this is your controller, and then that other controller for the motor working asynchronously at the same time, and this one will be moving while this one continues on. And like we're reaching the end of these notes coming soon, is that again worrying about the power considerations. And I've said this multiple times that servos, like a lot of the problems that come with projects, and if you look on other forums and other things that are out there, you'll see that there's issues that come from power, like power due to servos, and that was the real issue they were having. So it could be from programming and how you've set it up. So those weird pins like, oh, I didn't put my servos on 9 and 10 and I tried to put a light and it's not working, or something else that required PDOM and I have analog writes and it's not doing anything, because it will still compile, but won't work when it runs on the actual device. So like you need to deal with, okay, do I have insufficient power? And so that comes then, well, how much is going to be needed? So servos under load will require more power, and the common issues in all motors, and I've talked about that. And so like we need to then deliver this from some other kind of power source and some kind of other power circuitry that you have actually set up to deal with that. So maybe it's very basic. You've literally just hooked it up to, say, 9-volt battery or to AA's, or you have more advanced power, one that can handle kind of fluctuations and manage higher levels of what you're dealing with. So, and for larger projects, if you had more of them in here, you're going to have to worry about that and other problems that come up. Because the Arduino has a narrow operating voltage of that 5 volts or 3.3 volts from right here, and it's like sensitive to different variations that you have in that actual voltage itself. And it was designed more about the assumption that it's stable under 5 volt sources that are feeding the chip and the basics of it, maybe some basic other devices that are connected to it. But like with the Uno, like you can't expect it to then handle larger draws. You need to have a separate power source from this, because even when it's connected through USB, like we've been doing generally, that's one level of power versus powering it from an actual battery. And that's where, again, when you start adding more and more motos, not like this week, but if we had more in the future, then you're going to have separate circuitry between the two of them, and basically some power sources. So those are the basics from there in that USB, but you'll get more something like this. Why I want to jump ahead quicker here is, say, examples that you could get something that's hooked up this way. That you'd have the Arduino Uno, you have a common shared here that each servo, the 3 pins, black here being the ground, is that they're all connected to the ground for the external power source, and this ground is also connected in some way from the Arduino to that same common ground. So it's still one common ground for the actual circuit, but then the power itself is that, well, the Arduino is going to be powered through like the USB jack or through the barrel jack or through this VN kind of power from here, and then the servos themselves will be drawing their power from something separate that's connected to this positive line for here. And then your control lines, you can see here, they have all of them, like 1 pin 9, and then they have the others on other PWM pins from there. But here we still have to know if we're using servo.h to control these, then this pin cannot be used for any analog writes or anything else. If we go to then seeing kind of like a physical wiring of this is a similar kind of idea of what we saw in that last picture. We don't see the power source here, but they've probably just got it hooked up like to some AA batteries of 4 of them or more of them to be able to run these 4, but they're running separately from here. And here you can see the shared, that they got the ground here. Here's us attaching to the shared ground. You have the PWM pins that are coming in here, and you have these connected in through a breadboard just to make it easier. You could have directly had some of these connected here, but it's just making it easier to connect from the standard servo and get it into the actual board. And I'll explain, when you're looking at the servos, they don't actually have kind of like those M prongs that come out that make it easier to plug into the board. But in the kits themselves, there are other things that you can use. You can even kind of modify and try to get like an M2M cable plugged in to get that working. But I'll show, if you have the Freenove kits, that like what is one of the components you see in there and how can you use that. Over here, you can see that this is an example of servos. We have like 4 of them hooked up with separate names, and then each pin here matching up to the pins that they're connected to from there. Now, as we come here to the end, here's a picture of the actual servos that are in the kit. So, and I've seen these a lot, these Tower Pro SG90 specific servos. Like these are the hobby kind of standard / micro servos that we are seeing in the kits that we're working with. And once again, just like with the ultrasonic, here's like some extra information you look up to it. Like oh look, it needs 5 volts from here. The torque is 2.5 kilograms per centimeter, and I'll explain that in the next slide, and we'll hopefully have examples in the future. This is kind of how much torque or like pressure, like what does it load that it can handle, and this is per centimeter, which is going to be the further away you are, the less weight it can hold versus closer to the specific shaft itself. The gears in it are plastic. Most of the time that's easy to see because they'll be in this kind of translucent blue case where you can see the gears, you can see the basic DC small motor, you can see the little control circuitry that are in there connected to the potentiometer and so forth. You've got the 3 cables that are coming off from right here, and you'll see that most times like they'll be kind of distinguished, that you can see the brown in this case means ground, the red then means 5 volt power, and then what's usually the orangey yellow is your PWM or data line, and they're connected to these kind of socket plugs that are right here. So the insulator connected in, and so sometimes you'll see where that was easily plug into other devices. For ourselves, we're going to have to do something else to connect that to the actual Arduino. They only rotate from 0 to 180 degrees, and they weigh about 9 grams, which impacts how many you have and that kind of weight overall for your device. And the operating speed is roughly 0.1 seconds per 60 degrees. So how fast can it go from 0 to 60 degrees in that time? Now 0.1 seconds, it seems fast for us, but that could be slower in motors and also with our code in between. And you remember, these are running asynchronously. So the idea is when you're telling it to move, your code is running, and then this thing is taking actual physical time to move, and your code could have gone past where it, like basically it's running faster. And so 2 things kind of coordinating together. Now the last slide just talked about the torque a little bit, just so you're aware of it. You don't need to know this perfectly for now, but this is the idea when you start attaching stuff. So the servo that's here in the example, you can see this is the center shaft that they're measuring it. There's this accessory thing that's plugged into it. And now if you had something that's 1 centimeter away that's attached, so if you had a wire that was attached into this that's going away, and then say when the arm moves, that wire is going to move, and there's something attached to the other side, say like a door that's going to open or a flap or something. So like when the arm moves, there's going to be some metal attached to it. And so the idea is that 1 centimeter away, at max, it can roughly pull something that's supposed to be 2.5 kilograms. And that's 1 centimeter away. Whereas if you, let's see, if you suspended something on a load that's 0.5 centimeters, then the motor can pull 5 kilograms. So it's even closer. So if it was half this distance from where you place this, it can handle more of the weight. But then the further away that you make it from right here, it's actually going to be like less than the 2.5. So these are issues that come up then with these motors that you need to worry about. It's not just, oh, I have a motor and it can do everything fanciful. It's like, no. There's limitations that each of us have our own strength for how heavy we can lift stuff before we break ourselves or are unable to. Same for these actual servos themselves. Either you'll get that the servo itself just won't be able to do it, or you could actually, if it's not working properly, you could completely strip the gears at that time. So this is part of what you want to look up to, is like, well, if I'm building it and was it attached to, I then maybe should know roughly what's the measurement of the actual torque of moving that component or whatever weight it's on, and is that in the tolerance of the servo I'm working with, and maybe if it isn't, I should go to a different actually servo. For right now, we're just going to get the arm to move back and forth, so you're not worried about that. I would suggest even attaching very basic things to it, but don't go crazy. Don't break the 1 servo you have, or you'll be ordering another one if you want to work with them. Okay, So from there, we're done this part of the lecture, and we're going to be moving into, again, now the simulator video, where I'll go through some basics of the coding and wiring of the ultrasonic example, and then a servo examples, and maybe combining a little few things together with stuff we've dealt with before, and some of the kind of languages. And then the physical work, once again, I'll show you the differences of, okay, well, now if we've got this hooked up with the servos and the actual actuators together, and trying to get it to do a little bit of actual work in a closed loop cycle, what are different things that actually occur now that we're out of the simulator and working with the actual physical devices. So from there, I really hope that all of you are still doing good. I know it can be difficult, and usually by the time of this video, and I know right now, time of coding, it's midterm time, so make sure to check in on yourself and make sure that you're okay. Maybe stop and actually check on, maybe message a classmate or a friend you haven't heard from in a while and see how they're doing. You never know. It's always good to reconnect with different people. But from here, please go on to watch the simulator and physical videos together. Both of them will combine learning and adding to your knowledge. Bye-bye.